All right, so what I mostly want to walk through is how computer vision is now that LLMs have entered the game, and how we make benefit of it, make use of LLMs, make use of language entering computer vision, and kind of merge these two fields slowly over time. So I'm used to presenting with the laptops. All right, so this is how things used to be in computer vision for the longest of time before language entered the field. So you would build your you would build your database for training, and typically, especially if you do pre-training of a vision encoder, which is a model that should just understand images at a high level and that you can then use to do a task that you want, like fine-tune it on specific classifications or plug it into a detector to start detecting things and so on. So you used to pre-train these on large data sets where you have a list of classes that somebody made up, and then you have lots of images from this class, and then you pre-train your model, and then you take it and you fine-tune it on any specific task of interest, which can also be something else than classification, but here classification as an example. And then you have your final model for that task. With CLIP and much less known, but at the same time a line from Google, this changed completely. We basically how CLIP and similar models work, and I will say a little bit more later, but you pre-train the model, like not on this well-structured kind of data set, but on unstructured image and text pairs that you find somewhere, typically on the web, that are large scale. And then there is usually not even an adaptation fine-tuning phase anymore. You can just straight up, because it's combined with language that is relevant to the image, so you can straight up in language ask the model the task you want. Like for the flowers, you just list the number of flowers that you want in language, and then boom, you have your flower classifier. Maybe first question is, who knows how CLIP works? Very good. So I will go quick over that. So here's a more detailed view. So this was how typically basically all computer vision pre-trained data sets look like, right? And the list of classes is just something that at the start of a new project or collecting a new data set, usually PhD students comes up with a list of classes, things that they want the model to eventually learn about. And then for each class, they go do some image search on a few image search websites and then just collect the top images. And then you have this very structured grid. And maybe this brings another thing. So like the models that you learn on all of these data sets really only know about these things that the random PhD student just thought up at some point. Even more, like a real anecdote, MS Coco, which is like probably the second most popular computer vision data set ever, has 80 classes, and I think the classes are very famous. It's like frisbee, toilet, basketball, pizza. But what many people don't know is how did they come up with these classes. The senior advisors in the lab had children of the age like 8 to 12 or something in America, and they just asked them like, what are common things in your life that you like? And then the children said that, and boom, that become the 80 or the 113, I think, classes from Coco. And so all the models that we all computer vision people do all the time on Coco, they know about these things, like North American kid things. But luckily, this changed eventually with CLIP and the line, which said, okay, look, if we go on the web, we have tons of images of completely wild things that just people everywhere in the world took just because. And a lot of them actually are kind of annotated, but in free-form text. So for example, on the web, if you have the image tag, you have this alt text tag that is very initially was proposed for blind people so that they can read the description of what it is, but then eventually it was used by search engines and so on, that when computer vision was shit, to just know what the image is there. And so this actually was a very good incentive for web masters or people who create web page to actually write alt text that describes the image. And so now a ton of images on the web just come with this alt text. So this is great and bad. Bad because it's way less precise than the classic thing of having a list of classes and just getting images from that, right? You have stuff that can be completely useless, like thumbnail for version as of blah, blah, blah. So this doesn't describe the image, and there's a lot of that. But you also have really great thing, like very detailed things, like here. This is Frankfurt Airport skyline in 2017. Like no PhD student ever would have thought to make this a class in the dataset collection, right? So if we manage to train on this kind of data, then via the introduction of language, actually we kind of, I like to say, open up the vocabulary. Previously in computer vision, we always had the vocabulary of 80 things. And so the model know about 80 things, or maybe 1,000. Like imagine it was 1,000 classes and that was considered a very large vocabulary, and so models knew a lot, but really just 1,000 things. And out of those 1,000, 200 dog races. But now if we go to the free-form text from the web, we can essentially open up the vocabulary and have a model that can learn about everything, or at least everything that people write on the web, which is not completely everything, but a lot. So this is great. Then actually almost everybody knew how CLIP works, so I'm gonna skip that and spend some time on a more thing from later. Maybe a small mention. So CLIP, I know how many people know. How many people know SigLIP? Okay, super, way fewer, super few. So SigLIP is a variant of CLIP that we developed in the lab. It's basically a simplification that is then easier to scale up. And the SigLIP checkpoints are all available for free also, and they are like just plain superior to CLIP on all metrics everywhere, and they are now becoming the standard in all kinds of uses. So if in any project you use CLIP, like just search on Hugging Face SigLIP and use that instead, and boom, you have free improvement. The method of how it is changed, so you know this picture from CLIP, right? You embed the images, you get the image embedding vectors, you embed the texts, you get the text embedding vectors, and then you do contrastive, like softmax classification in that direction and in that direction, right? How we simplify this is we say, okay, don't do like softmax across rows and columns, but instead look at each individual pair of image and text as a yes-no classification task, just binary cross entropy. That's why SigLIP, sigmoid CLIP. And so this is basically now a pointwise loss. Right? Each pair is an individual point independent of the others. So this gets rid of difficult things like normalization across rows and columns that you have in the softmax. This makes it much easier to scale this and compute this across many devices to go to very large batch size, and so it makes it easier to train a better model at larger scale. Right, so that is one thing, and most vision language models, maybe 2 years ago or so, all used CLIP as image encoder, and now lately they are all changing to SigLIP as image encoder. All right, then let's actually skip that. Right, here's some examples of like what you can do with these models, and just I'm gonna just pick a few to show how really good these image text models are nowadays, actually. So for example, most of these images, like everything to the right, is pictures we took or generated that do not exist on the web when we trained SigLIP, so it's like truly new out of distribution thing. And if you look at, for example, I like this one, it's just us, the authors, and holding up papers that are printed SigLIP. And then embed this image through the image embedding, and then here just a bunch of texts that I wrote, each of them embed through the text embedding. And then here the score is, right, this image embedding together with this text embedding, how high is the score, like sigmoid classification between 0 and 100% tells you how well does it match, right? And here this matches very well a photo of the SigLIP authors, so the model can actually read it. It doesn't know the SigLIP paper because it was not out when we tested it, so it doesn't know our faces, but it can actually just read this text and give a high match then. And also this one is fun because a photo of researchers at Google Brain, it gives a very high score, and at OpenAI it gives a low score. How can this possibly know it? What you don't see here is like this is our office building, so up here is a small Google logo. And it picks up on that. So these models are good, but in general for SigLIP, but also for CLIP, the more precise your text is, the higher similarity score you will get. So I have this example here with the cow on the beach. Let's say this one or this one. If you just say cow, you get a reasonably high score, but it's like 30%, so it's definitely more than 0, so there is a match. But this is a very general text, so the score is usually low because it matches with tons of things. And as you get more precise, you get higher score. Like a cow in a tuxedo or a cow on the beach fits this much better, right? So you can actually, this is especially good for very fine-grained things. And these type of models are now widely used in photo search. If you want to search your photo library for specific things, for example, nowadays you can do that. In the past, you could just search for like 1 out of 20, 30,000 classes that people came up with first. Cool. Then there is a multilingual version of that too that you can try and download, which for original clip didn't exist. So if you're especially interested in multilingual, multicultural image text things, just go for SigLIP. There is no special modeling ingredient. It's just from the web data. We find images and text from all languages, right? So just be clear to not filter out non-English examples, which a lot of clip papers and models do. But we trained one which just didn't filter by language, take everything, have a tokenizer that is multilingual, and then boom, you get multilinguality, again, almost for free. All right, so this was about contrastive learning. And this is how pre-training of image encoders has largely been done in the last few years, basically since CLIP. Because, you know, with the addition of language, now we can get the image encoders that know many, many more concepts. To be fair, there is a second big paradigm that doesn't make use of language at all, Dino, which is also very popular to be done. I would say Dino and SigLIP is like the two major ways to pre-train image encoders nowadays. However, there is a major flaw in CLIP and SigLIP and basically all of the contrastive image encoder pre-trainings, and I like this example to show you this flaw. Actually, how many people know what I'm gonna show next? I'm just curious. Okay, good. So if you have this example, you have this picture and you have a perfectly fine description of it on the web. This is a cat sitting left of a dog, right? Now just imagine you have the image encoder and the text encoder, and you have a mini batch of pictures with tons of other images and texts, right? How much does the model need to learn, or what does the model need to learn to understand in order to satisfy the loss? And now think more of CLIP than of SigLIP, because it's even worse with CLIP. So right, so with CLIP we have this picture and all of the other texts. This is one of the loss directions, right? And it needs to pick out this text out of all of the other random texts from the mini batch. Now what can happen? So if there is no other cats or dogs in the whole mini batch at all, then the model only needs to pick up on the word cat. It can ignore all the rest because there is no other cat. It can perfectly solve the training task, right? So the model can be really lazy. For it to learn to pay attention to cat and dog, there should be another image in the mini batch which has just a cat, not a dog, and vice versa. And then it's forced to solve this task in this mini batch to pay attention to both words, cat and dog. All right, so maybe there's a chance of this to happen. Usually the mini batches are like 32,000 random images, so there is a chance that this happens. But now, to learn that they are sitting, right, what does there need to be in the mini batch? Another picture with a cat and a dog that are not sitting. Only then is it any useful to pay attention to the word sitting and start to understand what this means and how it connects to the image. Even worse, left off. Right, for the model to actually need to learn left off from this CLIP supervision task, there needs to be another picture with text in the mini batch that has a cat sitting right off a dog, or a dog sitting left off a cat. Right? Otherwise, there is absolutely no reason for the model to learn what left off means. And this is a major flaw in these kinds of models, the contrastive ones. Including SigLIP, although SigLIP a little bit less bad, but this is going to be too much detail. And a different type of modeling, which scales very well and just solves this problem, is if you pre-train with captioning instead of contrasting to other examples from the mini batch. So captioning, the model would look something like that. You have the image encoder, and then you have a text decoder, like autoregressive transformer decoder, whose task it is to just generate the caption, right? Like in language modeling, right? One token after another. Like always, I have seen these tokens so far, what is the next one, right? And if you think about it, this task is kind of much harder, or forces the model to actually learn about almost every single word here. Like, sure, some trivial ones not, like that you always start with the very likely, okay, sure, that's useless. But then to predict the next word, it needs to give high probability to cat or dog here, right? Because there is nothing else on the image. And higher probability to that than to any other words. Or it becomes more clear here for the left word, which is the most important part here. Right? If the model has seen a cat sitting, what is the next word? Here the loss really forces it to say left, to give a higher probability to left than to any other word in the vocabulary. So higher to left than to right, to in front, to behind, and so on. Right? So here, if you do captioning for pre-training, then the model is really forced to pay attention or to learn about all of the things in the caption, except trivial language things, like that of comes after left. It is unrelated to the image, so it's a little bit of wasted supervision, but whatever. And this, let's see, yeah, okay. So this we explored in the paper called the CapPa, Image Captioners as Scalable Vision Learners 2. So CapPa is for captioning in parallel. The parallel is a detail. It doesn't really matter. So there have been quite a few benchmarks that try to pinpoint this failure mode of contrastive methods. One of them was ARO, was one of the first, which stands for attributes, relationship, and order, I think. So they, let's see. Oh, I have an example coming a bit later. So it's a benchmark specifically crafted to show this issue of contrastive models, and they show that all of the kind of clip models perform really bad in each of these categories. So relationship would be the example of left off versus right off and these kind of things. And then, well, if we train with captioning, it basically solves most of this benchmark, right? A lot better, 100 would be perfect, but there is always some label noise. I actually manually looked into the errors. They were all due to label noise. And on some really good, although not perfectly solved. However, you need to be very careful when creating benchmarks in computer vision or in multimodal. So this is an example from the paper itself. I'm hiding the image here. I will reveal it later. But the task would be, which of these two captions correspond to the image? The horse is eating the grass, or the grass is eating the horse? Who says the first one? Who says the second one? Really? How do you even picture grass eating a horse? What's wrong with you? So, I mean, there is no way to picture grass eating horse. I mean, well, maybe nowadays with image generators, can a grass monster, or I don't know. But yeah, so a lot of this benchmark is actually solvable without looking at the image, just by looking at which sentence is more plausible. So this is a blind decoder that doesn't look at the image, it gets these scores. Right? So it doesn't mean that CapPa is useless, right? It still gets more than the blind decoder, but it means this benchmark is not actually, doesn't really test that you look at the image properly for vast majority of the test cases. And this is like one example. There have been multiple in computer vision. There was a visual question answering, or multimodal actually. There was a visual question answering benchmark, which is just in general questions about the image. And the first version of it was also like, was used a lot until somebody was like, hey, let me just use a language model to answer these questions. And then it got same score as all of the like multimodal models or methods. And so again, it was because for all of the questions, without looking at the image, you have a very plausible answer. So this is a very important thing to keep in mind when doing benchmarks for multimodal. Like always, if you look at just one modality, can you plausibly answer this? And one good way to get around this, which then some other works has done, for example, here one that was called Sugar Crab, which is essentially a improved or fixed version of this ARO benchmark, is to go by categories and then, let's see, yeah, and then always make sure that you also have the opposite in the image. Do I have a good, I don't have a good example. Like, this would be a bad example because you cannot have the opposite, but if it was like the cow is eating the grass is the other one, right? Then you can have, like, both are equally plausible without looking at the image, right? And then ideally you have both in the benchmark. You have once the image with the horse and once the image with the cow, and these are two examples, and you need to get both right. And very recent multimodal benchmarks are starting to do this, and suddenly be much more difficult to solve by models. However, good news, CapPa is really good on this fixed benchmark also, like essentially solving a large part of it. Yeah, so I think we should all be pre-training by captioning nowadays and not by contrastive anymore. Maybe if there is like one question at this point before I jump to next topic. No, okay, then I just jump to the next topic. Which is not unrelated. It's like now we have seen how we pre-train image encoders and how they are connected to language, and hopefully how they kind of start to understand what's going on in images. Now I want to give you an overview of how current modern VLMs actually look like and how they are trained and how they work. So I'm going to use our line of work, which is called PaLI, just to exemplify this because it's what I'm most familiar with. But most of the VLMs that you hear about, Lava is I think the most famous one, they all look kind of similar or the same gist. Who knows about PaLI? Okay, not too many, which is good. Because those who raise the hand, they should really be in the other room. Most models look somewhat like that. It's basically the API is the same for almost all of them. You have input an image and a text, and output some text, right? And you can put surprisingly many tasks in this format. The input text could be an instruction, like caption this in Taiwanese. There you go. And then the output would be the thing in Taiwanese, but it could also be a question about the image, and many image understanding things can be formulated as questions, right? And then the answer would be a text. What this doesn't cover is if you want the model to also generate or modify the images. And this I'm not covering in the talk at all. This is like a completely separate line of work. All right, and how this is usually, all of these models are usually trained, is you take existing pieces that have been trained in isolation before, you stick them together, and then you tune them on some mixed modality tasks, which I will talk more about in more detail later. So for example, in the PaLI line of work, we take a pre-trained vision encoder, which actually this is like 4 different papers, I think, PaLI papers with just different versions of the model. And over time, which vision encoder to be used changed. One of the things, the early works used exactly what I mentioned earlier, a vision encoder pre-trained on classification data set, which large amount of classes, but then switching to a, for example, SigLIP encoder, was a huge improvement there. You could have same or better quality with a smaller model just because it's trained to know and understand about a lot more concepts before, right? And then usually you have some kind of language model that you stick together with this, and the language model is also usually pre-trained. In the early works, this was T5 or MT5. Later it became UL2, which is like kind of an improvement of T5. And even later it became decoder only one gemma. So just a couple examples of tasks that you can imagine doing with these models, and these are real model outputs. And again, this shows like the nice flexibility that language brings over just lists of classes, right? Here you can ask how many coins are there, but you can also be more specific in any way that you want, like how many $1 coins are there, and then it counts just the $1. Or maybe you could ask how many dark coins are there, right? You can come up with all kinds of things that nobody would think of up front. Or yeah, like ask it to read some of the text or understand the picture. You can also start doing multimodal in context learning, although I don't want to dig too deep into that topic, but in general these models are able to do that in the sense that you give a couple input-output pairs in the context, like as input, and then you give a last input and you ask it to do the output in the same style as the input-output pairs it has seen before. And this is like, just think of it the same as language models. You learn to do next token prediction, and so what is the most likely output after this, after having seen all these, or it's the answer in the same style as the stuff before, right? All right. Then the problem with PaLI, and also one of the reasons why it's so actually not that known, is these were all models that we trained at Google, and then we write the paper about it, but we don't release the model, we don't release a demo, nothing, just the paper. So you basically, they are really good models, but you have to take our word for it. And we use them a lot internally for many other things. They are really good, but how would you trust this, right? And what can you do with this? Because you cannot retrain them. We didn't even tell the details of the data, how to train it, right? So after a couple years, we understood that, and we worked on an open one, which is called the PaLI Gemma. And this one is open, you can download it, you can use it, and we wrote a report that goes into a lot of detail, not completely everything, but a lot. And here is where I want to talk a little bit more how this works. And this is the one that is actually also most similar to other models that exist of that type currently, like Lava, Cambrian. I don't want to enumerate them because now I will forget a couple. There have been quite a few very similar models recently that are all pretty good. Moondream is a nice one also. So yeah, as I mentioned, you have an image encoder that was pre-trained in some way. And then nowadays, usually just a transformer decoder language model. So you send the image through this pre-trained image encoder, and then you get a list of tokens there, of like a list of float vectors. Right? They represent the image, or a grid of float vectors, but then you flatten into a list. And you have the text, which you tokenize through your tokenizer, and then you embed with this first vocabulary embedding matrix of language models, and then you also have a list of float vectors, right? If they are not the same dimension, you multiply them with a matrix to make them the same dimension, and then you just concatenate them all. And then you have a long list of float vectors that is both your image in some already well understood in quotes representation, because this image encoder was pre-trained to give you a good meaningful representation of the image, and maybe less well understood but somewhat the text, right? Because you also use the vocab embedding from this pre-trained decoder. And then you just give all of this to the decoder and you make it continue. And what I forgot to say, this text is both input and output. So you have an input text, but then you also have the expected output text. In question answering, that would be the answer. If you give it an instruction, like caption this in Taiwanese, then would be the Taiwanese text of it, right? This also, so if this is just an autoregressive decoder going from top to bottom, then the output, you would also tokenize it, concat it here, and then put the loss on it. So here is this maybe in a better picture. So this is the attention and the input output. So you have the image, then you have beginning of sentence token, then you have the input string, which is the question or the instruction, and then you have the output sentence string, which is the answer. And you tokenize them all. And then one thing that we said, that we proposed here, and I think everybody should do, and I think everybody will do, is that on all of the inputs you can have full attention, and only on the outputs you need autoregressive attention, because that's the only thing you need to predict, right? And so you just let the question also look at the image, but the image tokens can also look at the question, and then can become more relevant to the question at hand as you process through it, right? And then this whole thing is just trained with next token prediction, just like language models, but now on a multimodal data mixture. So we try to make it very clear, this kind of multimodal language models, or VLMs or MLMs, they are trained in many stages. So we try to make it clear, and this is true for almost all of them. So there is the first stage, stage 0, that nobody talks about, which is just for each component take a already pre-trained off-the-shelf model. In this case, it was SigLIP for image encoder and the Gemma for language decoder. So this is basically free for you because you just download it. Then the first stage is multimodal pre-training, where you try to collect a large mixture of multimodal image and text data and formulate it as a kind of task that fits this model. And you try to go broad such that the model learns to align these existing models on many topics as possible. For example, the simplest one is captioning. You just take all of this image text pairs from the web that I talked about before, and then you do captioning, right? And then the input would be just caption this in, and then the language, and the language you can auto-detect from the caption with some API, right? And then the output that. But you can do other tasks and add them to the mix, but maybe a bit fewer. I will show in the next slide. Then one thing that is very common in computer vision, but I think multimodal and language model people didn't know this so much, is that one very simple way to get a much better model is you train for most of your time at some resolution, usually 224 square or 256 square. But then towards the end, you increase the resolution of the image, which has two effects. One is that you see smaller details better, obviously, in case that matters for the task. The other one is also you increase your sequence length a lot, which is the model capacity. So the model just becomes a lot stronger model. And so here there's also like two resolution increase stages. And then there is finally the transfer stage, which means fine-tune it on the exact task that you care about. Which can be something very specialized, or it can be chat. If you care about making a chatbot, then you get afterwards a data set of just chats, and then you fine-tune on that, right? And what is most papers do is instruction tune mix is like their final task that they care about, which is kind of hybrid between chat and question answering, and so just throw a lot of smaller, high-quality data sets together and train on that. All right, now to the training mixture, how this is trained. One thing, this is the training mixture of PaLI Gemma. I didn't put the order of magnitudes. So one thing that I said is captioning. That's very easy. I just described how you can get a lot of data for this. So this is also by far the largest fraction of this data mixture. Then if you have a OCR service, like classical computer vision OCR methods are really good already. So you can have a lot of images that you got from the web or from random source and have just some classic OCR API. All of the big cloud providers have that. Go and have it annotate text that appears in the image, and then you can add this as a task into your mixture, right? Maybe the instruction is read the text on the image, and then the string is whatever the OCR method output. And you can add this in the mixture as a task. There has been a paper from colleagues who are co-authors on that, which developed a method to turn a caption into a bunch of question-answer pairs. It's relatively heuristic based on English language, but you know, there's like if you can identify in a string what are the objects, then you can formulate what questions about it and things like that. So there's like 4, 5, 6, I don't remember, heuristics of how to turn caption into kind of questions with some specific structure. And that way you can turn captioning data if you have good captions. So you filter your data set first to good captions, and then you turn these into a bunch of question answers. And then if you want to be multilingual, you can also randomly translate some of these with machine translation, which is pretty good nowadays also. And then you have a multilingual question answering data set that you can throw into the pre-training mix. Here is a few examples also of like more specialized questions. For example, if you have a detection data set, or you have your data set, you annotate it with a detector, then it gives you what objects are in the picture, right? And then you can, from that, generate these kinds of questions, all of them, right? And then throw this into the mix too. So as you see, I think this is the current state nowadays. Like there is a lot of work into the data mixture creation and just coming up with creative words to generate more data, creative ways, sorry, to generate more data to train on, to give the model the capabilities that you would like. Personally, I think the modeling, we are good. Like just have this kind of autoregressive transformer and a good image encoder and you're good. This kind of model can learn almost everything, and the big question is like, how to make it learn the thing that you want, so which is how to generate the data that gives it the skills that you want. All right, and these are just a few examples of what you can do, and you can, with any skill that you want the model to have, the main question is how will you generate data that teaches that to the model. Yeah, let's not go through everything. There is a few interesting one, detection and segmentation. I want to talk a bit more on the next slide, I think. And then, yeah, good tables, the model is good, we don't need to go there. One interesting thing, though, I want to highlight is I make it sound like the silver bullet. It is almost the silver bullet, but not for everything. So the TLDR, it's these kind of models are good for things you find on the web, not for things you don't find on the web, kind of obviously, but it's worth saying. So for example, here in our long list of tasks that we then evaluated on and so on, there is a couple data sets, RSVQA, which stands for Remote Sensing VQA. This is satellite images, and the questions are like, is there a lake, for example, right? But from satellite images. And the model performs really well there too. Like this is 93% out of 100%. However, we do some ablations. Here, these are all of the tasks are the different curves. X-axis is we reduce the amount of multimodal pre-training. So this mixture and this stage one, right? We do 1 billion examples of this in general, so we start here, and these are the numbers of all of these tasks. And then we see for each curve is a task, how much does it deteriorate as we do less and less of this multimodal pre-training. And you see many tasks do deteriorate, right, as you reduce the multimodal pre-training, so the multimodal pre-training helps. However, there is a couple tasks which just stay at the top, which means that the performance doesn't deteriorate even if we go to 0 multimodal pre-training, which is exactly these tasks. So it means the multimodal pre-training is essentially useless for these. At least the pre-training that we did. So the most likely reason is that, and this is just same thing again, but in more detail from the appendix. The reason is in 1 billion random images from the web, with this data pipeline that I described before, it's just very unlikely for there to be useful satellite images in there. And so the model doesn't benefit from it and doesn't know about it. Okay. So that's one thing to keep in mind. Probably like web scale pre-trained model will not be useful, at least out of the box, for a medical imaging task. Because, okay, there are medical images on the web, but not high quality, not many, especially in 1 billion images, maybe just a few thousand. Okay. And the last thing, so you may think, okay, but this is all with text output only, but you said something about computer vision. Where is the computer vision? This is just question answering captioning. Computer vision used to be a lot more, at least detection, segmentation, but also other things like depth prediction and so on, and that doesn't really fit this API, so what are you talking about, Luca? You can make most tasks fit this API. So let's look at an example of detection. And this was first introduced by the Pix2Seq paper. This picture is from one of the PaLI papers. You can actually write detection boxes as text. So you just divide the image coordinates. Let's say you discretize it. In no matter the size of the image, you say I have from 0 to 1023, so 1024 indices in X, 1024 in Y. And so each box is described by 4 values, like the X and Y bin that the top left coordinate falls in, X and Y bin that the bottom right coordinate falls in, right? Now you have your language, like the vocabulary, you just add 1024 tokens at the end and you call them location tokens. And they correspond to each of these bins. And then you have an image like this one, which has detection boxes as annotations. So it's like the thing that it is plus the box. And you just turn it into this string, which is the 4 coordinates of the box with these new location tokens. And then the text of what is in this box. And if you have multiple boxes, well, you just concatenate them. And there you have your detection task as a text prediction, like a captioning task. So it fits perfectly the API, and it actually works well. So we do this, and we can do this with almost all vision tasks. So this maybe you can say, okay, but look at this was just a list of boxes, like sure, you can turn coordinates into text extra tokens, but what about segmentation? The output is, who knows what is semantic segmentation? Okay, who knows what is panoptic segmentation? Okay, so you all know semantic segmentation. Panoptic segmentation, you have a second layer that you need to output for every pixel which ID of the object it is. So do I have an example? Oh yeah, right here I have the example. So let's say you have multiple elephants here. If you do semantic segmentation, the pixel output of this elephant would just be the class elephant, right? And of this one also the class elephant. If you do panoptic, then you have two layers of outputs. One is the class elephant, like in semantic, but the second one is the ID of the elephant. So this pixel would be ID 1, and this pixel would be ID 2, and this pixel would be ID 3. Okay, so that you can separate the individual instances of the same object. Yeah, and like there is no way you encode this in text. Like this is a lot of pixels with a lot of values each. However, there is a way, and we did this with a very nice motivation that I will skip and go for the simplified version in the UViM paper, and at the same time a few other labs did that, and now also other labs converged to doing the same, which the short version of it is essentially learn a new small vocabulary that these kind of, your ground truth can be encoded into and decoded out of. And to learn the vocabulary, discrete vocabulary in autoencoder way, the best tool that we have currently is VQVAEs. Who knows VQVAEs? Vector quantized VAEs? Okay, I don't have enough time to fully explain it, but who knows just plain autoencoders? Okay, so imagine the plain autoencoder, but your bottleneck, you have a special operation that discretizes it. And then you have VQVAE. So if you have an autoencoder of an image, maybe in the bottleneck you have a grid of vectors, but smaller than your input, right? And then on the side, you have actually I have a slide on this, but much later I think. Let's see. Yeah, here. So this is autoencoder, encoder, decoder of the image, and here is your bottleneck, and it's a grid of vectors. Now on the side you have a dictionary that you want to learn, which is just a bunch of vectors that you randomly initialize. Let's say you want dictionary size 1000, so 1000 random vectors that you initialize. Now in your bottleneck, each of the vectors you have, you just look up in the dictionary what's the most similar and you replace it by that. And that's it. And then you have some special losses that make the dictionary ones be learned to be more similar to those that are encountered here. And the decoder reads those and decodes and regenerates the image, but that's the very quick gist of vector quantized autoencoder. And this way you have an autoencoder that generates latent code or bottleneck that corresponds to vocabulary entries in this vocabulary, right? And that is very similar to tokens in language, right? Then you can imagine this dictionary, you just add it to your vocab embedding from your language model. And then you have your language model learn to predict those, and then those can be decoded again into a picture in this case, but more relevant segmentation here. So that's the thing you do. So you basically learn to encode into dictionary or into a vocab, discrete vocab, your ground truth labels. So your panoptic segmentation maps or your semantic segmentation maps and so on. And then each ground truth corresponds to basically a string of these dictionary entries. So this is text, like just that it doesn't happen to correspond to English words, but to words in your VQVAE's dictionary. Which can then be decoded. And so you can have a language model that gets in as input a regular plain image, and then auto-regressively generates these codes. And these codes can then be decoded by the decoder part of this VQVAE into your like special structured ground truth, like your panoptic segmentation map, your semantic segmentation map. And so basically anything you can give to a VQVAE, you can turn into the language, in quotes, that you can append to your language model's dictionary and then learn as part of your multimodal model. And that's how we all now do these advanced vision tasks with VLMs. Yeah. And so in this work of us from a few years ago, UViM is Unified Vision Model. It's basically this model, and the exact same model can do all of these classic vision tasks reasonably well. So here we have a panoptic segmentation, depth prediction, or colorization of grayscale image. And they're all the same. Like you take the ground truth of the training set, of course. You learn a dictionary on it to encode and decode the ground truth into the vocabulary. And then you learn a language model that maps the image to this code. And then you decode it with your VQVE decoder. And so you see, this is like the exact same model structure for all of these tasks. And the model structure is really a language model that generates this language. And then if you want to decode it, you add the decoder. So this fits perfectly VLMs, because this is basically a VLM, but just in this case, it doesn't have language input, right? But if you now say, okay, predict the depth of it as instruction, then you have here your VLM with your language input. It generates this language, and then you have a depth decoder or a panoptic decoder, and so on. And this is how we make VLMs do advanced vision tasks that don't obviously map to text, but now we can map almost all tasks to text. A quick final one, and then I will stop and open for questions, is that when we do this autoregressive next token prediction, which is all that we do now with VLMs also, just the same as in language model. Now everything is actually the same as in language model. What this means is just, this is a form of imitation learning. You have your data set of tokens and your model learns to predict the same tokens, right? However, especially if we go to these fancier methods which encodes panoptic segmentation masks into tokens, or even think of just the detection boxes before. Yeah, this example is with detection. Let's go with detection. Then this task is not really what you care about, right? That you get this sequence of tokens exactly right is not exactly what you care about. Think of the case where your ground truth says this box is at location 500. The 500 is a token, right? So the task, the next token prediction task says you really need to say 500 here. If you don't say 500, if you say 501, it's wrong. If you say 500, it's correct. But if you actually think of the detection task itself, we don't care, like if this box is 1 pixel off or not, this is perfectly fine, right? So the task that we use for training these models, especially for the more advanced tasks, is not really the task that we care about. And the model has no way of knowing this. One very nice way that we show here for vision, but language people also do for language, to get your model, your LLM, VLM, or so on, to tune it to the task that you really care about in the end, is to do a bit of RL on top of it afterwards. Because the thing is, the task you really care about is usually not very differentiable. So I think detection is the simplest one in computer vision. It has fancy metrics that really summarize well what we care about for detection, like MAP, which includes things like the intersection over union of this box with the ground truth box and so on. Tons of non-differentiable things. So we cannot just gradient back through that metric that encompasses what we really care about. And so we need to do RL. So this is now a very common pipeline to first train your model with next token prediction such that it performs reasonably well on the task, but maybe it doesn't nail exactly what you care about. And then you use this model that is a good model as the start. You sample a bunch of outputs for an image, and then you have your metric that describes what you really care about, or it could even be your human that describes what is better, that scores each of these outputs. Right? And then you have a score for each of the outputs. You basically, quick version of RL is you take the best one and you say, please sample more like this. So it's your new ground truth, and please sample less of the worst ones. And that's just a very simple RL, like this old, what is it called? Reinforce from 92. And that works really well. And why is this now a thing and not a thing in 92 when this reinforce in RL was invented? Because for this to be able to do reinforcement learning, you need to be able to sample multiple plausible outputs for a given input such that you can do RL such that, because there needs to be one sample that is better than the other of the output, right? And this is a recent thing. In vision, only with the appearance of these VLM style models, where it's very natural to sample multiple outputs. we can do this. Like the classic vision models, faster RCNN, deep lab for each individual task, they couldn't sample multiple outputs, so RL tuning wasn't even a question or an option. Yeah, and that works, that improves them a lot, but I will stop here. The main conclusion for this I want you to take away is that like vision and language are actually converging. We're starting to model everything in the same way with the same model, which makes it very easy to combine these, which turns the main question is not really a modeling question anymore, but more a data question. Like if you can combine these models easily and learn them easily, so how can you now formulate the task with multiple modalities that you really want it to do easily? And that's it. Thank you.